Yeah, so I'm Saheli Biswas. I am a research scientist at the CSIRO, Commonwealth Scientific and Industrial Research Organization. And today I'll be presenting on material challenges with proton conducting ceramics for intermediate temperature, hydrogenation, dehydrogenation applications. So we are basically the electrochemical energy technologies team, and we are working on both low and high temperature electrolysis regime. So as we all know that down the decades, there has been constant efforts to gradually move from fossil fuels to renewable energy. However, with renewable energy, there are still certain challenges, and the major ones being intermittency. So depending on the location where we are, or the time of the year that we are passing through, the renewable energies may or may not always be available, like solar or wind energy. And then again, storage issues are there, and obviously transportation. Now, so to address these issues, a lot of technologies have been emerging, and the power to X technology happens to be one of the main backbones. So here what happens, the renewable energy is directly utilized to convert water to hydrogen or other valuable hydrogen carriers like methane or gasoline or methanol or even ammonia. And all these chemicals can be either stored or they can be transported, and they can be utilized for different purposes. Now, the major types of electrochemical cells include the low temperature regime and the high temperature. Now, in the low temperature, we have the alkaline or the anion exchange membrane electrolyzers, which operate between 25 to 80 degrees. Then we have the proton exchange membrane electrolytic cells, which operate between, again, 25 to 80 degrees. And then in the high temperature regime, we have the solid oxide cells. Now, depending on what kind of ceramic materials we are using or the operating temperature, the solid oxide cells can be of two different categories. One is the pure oxide based, like where the electrolyte that we use is an oxide ion conducting ceramic material like yttria stabilized zirconia or scandia stabilized zirconia. And these materials show appreciable conductivity in the high temperature range of 700 to 1000 degrees. Whereas there's another category where the electrolyte is a proton conducting material, ceramic material. And these materials show sufficient conductivity in the intermediate temperature regime of 400 to 600 degrees. And in today's presentation, I'll be mainly focusing on this intermediate temperature proton conducting ceramics for different hydrogenation, dehydrogenation applications. Now, proton conducting ceramics exhibit superior ionic conductivity because of the material properties in the temperature range of 400 to 600 degrees. So why this is more interesting is because this gives the direct opportunity to integrate the system with downstream industrial processes such as methane synthesis or ammonia synthesis or dehydrogenation of methyl cyclohexane, because these reactions also kind of take place in that temperature region. And in the industries, the waste heat is also available in the temperature range of around 300 to 400, 450 degrees. So what happens, as you can see in this picture on the right side, just a moment. So in this picture, we have the steam, industrial grade based steam available, maybe around 350, 400 degrees, that goes straight away to the electrolyzer. And at the air electrode, the steam is electrolyzed into protons and oxygen. Now, the protons travel across the electrolyte to the fuel electrode, where it can evolve as pure hydrogen. Or if we want ammonia, maybe then we can have ammonia synthesis catalyst on the fuel electrode side, purge nitrogen, then we'll get ammonia. Similarly, if we have CO2 and methanation catalyst, then we can have methane synthesis. Now, as simple as it may sound, there are certain material challenges, and as a result, this technology is still, I would say, at the low to medium TRL levels. Now, with regards to the materials, the most important material or the most common material that is used as the electrolyte is barium-based perovskites. Now, in this category, there are mainly two different kinds. One is the barium cerates, and the other one is the barium zirconates. Now, the barium cerates have high protonic conductivity. However, they are not stable at a little lower temperatures, and also they easily react with steam on carbon dioxide. However, barium zirconates are chemically very stable but they demand very high sintering temperatures for sufficient densification. And without densification, there can be gas crossover, and that also reduces the proton conductivity. Now, to take advantage of both the cerate and the zirconates, the commonly used material is composed is a solid solution of cerium, barium cerate, and barium zirconate. And then it was found that doping with maybe 10 to 20 mole percent alluvial rare earth element like maybe yttrium or samarium or gadolinium further enhances the conductivity. However, the most common material is barium, cerium, zirconium, yttrium oxide. Now, as I already mentioned, the advantage is that it has a higher conductivity in the intermediate temperature range. So if you see in this plot over here, the VI curve, so the current density is almost an order of magnitude higher with BCZY at 500 degree as opposed to the oxide ion conductor yttria stabilized zirconia. However, the current challenge is still the sintering temperature, because even with BCZY, the sintering temperature is as high as 1500 degree, and this limits the choice of electrodes, especially when we are having electrode supported structures where we are aiming to co-press the materials, like co-press the electrode and the electrolyte and then co-sinter. Then the high temperature limits the choice of maybe catalyst that you can use in the electrode. So one possible remedy is adding a sintering aid to promote low temperature densification. Now, before jumping on to what the sintering aid is and how it works, let's see how the densification affects conductivity. Now, in proton conducting materials, the way the protons are conducted or the way they travel across the electrolyte is via the Grotthuss mechanism. So what happens? The hydrogen reacts with interstitial oxygen through hydroxyl bond formation, as you can see here in this image, and then they undergo reorientation, break the bond, and then hop on to the next site. And then again, they rebond with the oxygen, forming the hydroxyl bond, and this process goes on, and that's how they are conducted. Now, in this whole process, or even like in whenever any ionic transport is taking place in a ceramic material, it takes place within the bulk of the grain and also across the grain boundary. So from one grain to another across the grain boundary and within the bulk of the grain. Now, if the material is not sufficiently dense, then the grains will also be underdeveloped, and then the ions face a lot of, like, the activation energy is very high, and the ions can't easily migrate across the grains from one grain to another. So this basically increases the ohmic resistance, and that drops ionic conductivity. And also in a recent study, it was shown through DFT calculations that whenever a proton is migrating, there are two activation energy barriers. So one is which the proton needs to hop from one oxygen vacancy to another. And the second activation barrier is basically the energy needed for the hydroxide ion to spin. Now, the first activation barrier is highly affected by the BCZY microstructure. So that's where the density and the grain size, the grain growth, how well developed they are, these things matter. So if the grains are not sufficiently developed, if they are not overlapping each other, then the energy barrier for the proton hopping is very high, and eventually that leads to a drop in the ionic conductivity of the material. So that's where the role of sintering aids come in to promote densification at lower temperature. So let's first look at what a sintering aid is. So it's basically a transition metal oxide, like maybe nickel oxide, copper oxide, zinc oxide, and which is added in a very low concentration to the mother material, which is BCZY. So as you can see in this plot over here, why these materials are chosen? Because they have ionic radii very similar to that of zirconium, and that's one of the reasons why they show favorable results when we are doping. This is not really, I would say, doping, but this is like an external aid, which then what happens above 1000 degrees, these oxides, they melt or become soft, and then they occupy the void space between the grain boundaries, and then it assists the densification together. So, however, there are certain downsides. So, if these materials are added in too much quantity, now since these are metal oxides, so in reducing atmosphere, they get reduced into metals, and in high concentration, they can lead to electron conduction pathways, and that is not something which is quite favorable. And also, these can react with the BCZY and produce unreacted, like unwanted phases, which can act as the impurity phases, and that also leads to a drop in the ionic conductivity. So there are other factors as well which affect the BCZY densification and conductivity. First is the powder synthesis technique. So one is the weight synthesis technique, where all the precursors are added in a liquid solution, and then it can be either a sol gel method, or it can be a co-precipitation method, or even the Pecchini method, or it can be dry synthesis, where all the powder precursors undergo thermal treatment in the powder form itself, and then the phase evolution takes place. Now, the next thing that affects the BCZY densification is obviously the powder particle size, then also the sintering aid addition technique. So here there are two pathways again. One is the in situ addition, where the phase evolution of the BCZY takes place along while the sintering aid is already there present. So the sintering aid is added at the very first step, where we are preparing the liquid solution with the precursors of BCZY. And the other one is the ex situ addition, where the first BCZY is synthesized through whatever method we want, and then the sintering aid is added via either dry milling or wet milling. So this is basically ball milling or any other mechanical milling process that is used to add the sintering aid to the BCZY. And then next is the sintering profile. So that has a huge impact on the densification and conductivity, and also the cerium zirconium molar ratio in the BCZY composition. So first we will start with the powder synthesis technique. Now, ideally the powder that is synthesized, the BCZY powder, that should be any agglomerate free, because studies have shown that with increase in the agglomerate volume fraction, the density also sharply decreases, which is not quite what we want, because that then negates the effect of all these things, that adding the sintering aid and doing everything. Now, ideally spray drying is a helpful technique that helps in getting rid of all those agglomerates. However, for bench scale studies or even like lab scale studies, this is something which is not very cost effective. So mainly there are two synthesis techniques, as I already mentioned. Now in the wet synthesis technique, the agglomerates that are formed are soft agglomerates. So these are particles that are just touching each other via adhesive repulsive forces. So these agglomerates can be easily broken down when the material is pressed, like it can be isostatic press or uniaxial pressing. So when the material is pressed, compressed, and then that time the agglomerates get broken down. So this results in higher densification during the sintering step. However, in the dry synthesis process, the agglomerates that are formed, these are basically hard aggregates. So they have a bridge in between them, like you can see in this figure, and these particles are like individual particles are like clubbed into each other. So they can't be broken down easily, and that basically leads to lower densification upon sintering. Now, some recent studies have also shown that the strength of the agglomerates follow an inverse relationship with the primary particle size. So this makes it difficult to compact nanopowders and for heterogeneity of microstructure prior to sintering. So more in-depth studies are needed to actually find out the effect of how the agglomerates and the shape and size of the agglomerates and how they are affecting the sintering technique, or both co-pressing, co-sintering, or even if you are going for any deep coating technique, like if you are not planning to press, if you are going for any electrolyte other technique like tape casting or deep coating or spray coating, there also these agglomerates can affect, and more in-depth studies are needed for that. Next is the effect of the powder particle size. So in a recent study, it was shown that the same electrolyte material, when it was ball milled, leading to an average particle diameter of around 300 nanometer, then it gave an overall power density of 350 milliwatt per centimeter square, whereas when the same material was nanomilled, that is milling at a much higher rotational speed, the particle size was crushed down to 131 nanometer, and that gave 400 milliwatt per centimeter square power density. So the thing is, the nanomilling, that is a higher rotational speed during the milling process, that is not only reducing the BCZY particle size, but it is also helping in mixing the whatever other sintering aid you are having there, or maybe other catalyst particles you are having there. So that is more uniform distribution is being created, and that kind of uniform distribution also helps in the sintering process. So, and especially for electrolyte slurry coating techniques, like if you're going for spin coating or brush coating, dip coating, spray coating, or even tape casting, the powder and particle size is really, really important because it directly affects the viscosity and the coating uniformity and densification. So, in this regard as well, a lot of streamlined studies are needed to clearly understand the effect of the powder particle size on densification, whether it is for co-pressing, co-sintering process like dry process, or if you are first preparing your electrode or support material and then casting your electrolyte in a liquid slurry form. Now, the next thing is the effect of sintering aid addition technique. So, as I already mentioned, there are two pathways. One is the in situ addition. So, here the sintering aid is added very initial step during solid state reaction or sol gel method or maybe co-precipitation or exolution. So, this gives a more uniform distribution because we are adding during the synthesis, like during the first step itself, and that leads to higher densification. However, in some cases, it also leads to complete dissolution of the sintering aid into the lattice structure of the BCZY. So there has been, like, so there in literature will have shown where they have used the sintering aid and that has removed the cerium or the zirconium from the BCZY lattice quite a bit, and that has led to subsequent proton trapping effects that drops the conductivity. So if you see in this figure, so this is the total conductivity in hydrogen. This is the second one is the grain boundary conductivity in hydrogen. So here you can see they have used zinc, copper, nickel, three different sintering aids in the same concentration and with bare mother material BCZY, and the grain boundary conductivity is very similar for all four of them. However, the bulk conductivity is higher for BCZY and it has dropped in case of zinc, copper, and nickel, and that's because the zinc, copper, and nickel completely dissolve into the lattice and then replaces a cerium or zirconium from the lattice. So that's not something which is quite favorable. However, in comparison, when we have the ex situ addition, which is basically first you prepare your BCZY and then you add your sintering aid either through wet milling or dry milling. So this obviously gives less uniform distribution, leading to a little less densification. However, there is only partial resolution of the sintering aid, and this helps to maintain or in some cases even improve the conductivity. So this is one example where you can see that they have used BCZY and they have used the zinc sintering aid as well. And in case of zinc sintering aid, they have seen an improvement in the conductivity. So here also, I would say that more systematic studies are needed to compare the effect of different sintering aids when they are added in identical concentrations via both in situ and ex situ addition technique, because it is possible that there could be a certain regime, like maybe in the low concentration regime, the in situ addition is working better. However, in the higher regime, that is not. So then again, the sintering profile is also very important because depending on the sintering profile, you can lead to cracks and all these things, which is not very favorable. And the effect of cerium zirconium molar ratio, as I already mentioned. So I won't go through all the things because we are running out of time. And so in our group, we are focusing on all these activities. So far we have trialed out several electrolyte compositions. We have synthesized in-house and we have obtained very good conductivity results with high protonic conductivity, because this is also one thing which is missing. Like a lot of people are reporting just the conductivity, but it can also be oxide conductivity or electronic conductivity. So we need to focus more on the protonic conductivity when we are talking about these proton conducting materials. So those are the kind of research we are doing, and we are also working on the electrode development tailored for maybe methane synthesis reaction or ammonia synthesis reaction. So yeah, so we have these facilities starting from material synthesis to cell fabrication assembly, different characterization techniques, and obviously cell testing facilities. So this is our team. I would like to acknowledge all of them, and obviously our student vacation program where this student Shivesh Loganathan participated and did a detailed literature review in this area. So with that, I would like to thank all of you for your attention and happy to answer any questions.